David, it looks like you're on.
I am.
Should we conform to the usual MIT practice of starting 5 minutes late?
5 minutes. Yeah, that's right. That's right. I'm just looking to see whether there's Roman.
Yes, here. Well, you can.
And there's George. So I should say my plan is at the end of Lucas's presentation, I'm going to make a breakout room and invite the committee into it, and then we'll return to the main room to share. So let's see how. Oh, we're still a couple of minutes from 4:35. So there's a question of whether you're going eventually to send the slides to me so that I can post those on the seminar website. Very good.
David, you can see my slide, right?
Yes, that's the main thing.
Can you see some writing on it?
I can. It's not very coherent writing, but looks like my son's bank signature. So I'll make an advertisement to begin that next week the seminar speaker will be Clifton Cunningham from the University of Alberta in Calgary, and he's going to talk about unipotent representations and G2, and I forget the precise title. Today, we're very happy to have Lucas Mason Brown from MIT, who's defending his thesis here. And the title of his thesis, the title of his talk is Unipotent Representations of Real Reductive Groups. Lucas, thank you.
Thank you, David. Thank you all for coming. My plan today is the following. I'm going to start by giving some background on unitary representations, what they are and why we care about them, and some basic examples. Then I'll give a very high-level overview of the orbit method, which is one of the main guiding principles in the subject. This will lead into a discussion of unipotent representations, which are a small, mysterious class of irreducible representations which play a distinguished role in unitary representation theory. I'll first give the general idea of unipotent representations, and then I'll make 3 attempts to define them precisely. None of them quite successful. And then in the final part of my talk, I'll summarize the main results from my thesis and sketch a proof of one of them, which is a classification of the unipotent representations attached to the principal orbit. Okay, so to begin with, let's fix some notation. Let GR be a real reductive group. For me, this will always mean the real points of a connected reductive algebraic group defined over the real numbers. So it's useful to have some examples in mind. GONR is kind of the prototypical one. GONC is a real group by restriction of scalars. SP2NR, this is the group of 2n by 2n real invertible matrices preserving a symplectic form, and SONR. Maybe I should also pause to list some non-examples. Of course, non-reductive groups like the group of upper triangular matrices take the group, the orthogonal group over R. This probably should be regarded as a real group, but it's not under our definition. It's the real points of a reductive algebraic group, but not a connected one. Another example is the universal cover of SL2R, which is not algebraic in any sense. So our basic object of study is a unitary representation. This is a Hilbert space H, usually infinite dimensional. Equipped with a continuous group homomorphism pi from GR to the unitary group of H. And I'd like to give just maybe one example of what I have in mind. Say C is a compact homogeneous space. For GR. And we can take H to be the space of L2 functions on C. Actually, strictly speaking, to make sense of this, you need an invariant measure on C, which usually won't exist. And so there's this technical fix. Consider, instead of functions, you consider L2 sections of a certain line bundle of half densities, but this is not important. Nonetheless, this is a Hilbert space, and it has an action of GR. So the fundamental problem in unitary representation theory goes back to Gelfand. For a given real reductive group, GR, can we determine the set of equivalence classes of irreducible unitary representations of GR? This set is called the Unitary Dual. And this problem is called the problem of the Unitary Dual. So I want to just say a few words about the status of this problem. If GR is compact and connected, then its irreducible unitary representations are finite dimensional, and they're parameterized by integral dominant weights for a maximal torus. This is the standard Cartan-Weil theory. The unitary dual of SL2R was calculated by Bargmann in the 40s. The unitary dual of the general linear groups was computed by Vogin in the 80s. The answer is known for the complex classical groups. That's Barbash. And there are also some other low rank groups for which the answer is known. And I'm sure I'm leaving some groups off of the list, but this is a reasonable summary. I should also mention, thanks to the work of the Atlas team, we now have some software which can compute the unitarity of a given representation of a given group. But that's a bit different than having a satisfying theoretical answer to this problem. So one of the guiding principles in unitary representation theory is called the orbit method, or the method of coadjoint orbits. And this was discovered, invented independently by Costa and Kirillov. The idea is that there's some kind of correspondence between orbits of GR on the dual space of its Lie algebra and irreducible unitary representations of GR. And this correspondence, if it exists, should be something like a bijection. So the idea for this correspondence comes from quantum mechanics. These guys on the left are symplectic manifolds. If OR is, let me just write the definition up here. If OR is a GR orbit for some functional chi, then the tangent space to OR at chi is identified with the quotient GR mod the centralizer of chi. And we can define a two form, omega, using chi and the Lie bracket. So if A and B are elements of the tangent space, or are yeah, elements of the tangent space. And we just take their Lie bracket and then evaluate chi. And you can smear this around OR using GR, and you get a closed non-degenerate 2 form. So these are symplectic manifolds, invariant symplectic manifolds. These are, of course, Hilbert spaces. And symplectic manifolds are mathematical models for classical mechanical systems. And Hilbert spaces are mathematical models for quantum mechanical systems. And so we should think of this arrow from left to right as being some kind of quantization. And the arrow in the opposite direction as being some kind of classical limit. So instead of trying to make this any more precise, I want to give an example. Say GR is GONR and fix a partition P of N with K parts. And let nu be a K tuple of real numbers. Then the data of P and U defines a coadjoint orbit corresponding to the Jordan normal matrix with block sizes given by P and diagonal elements given by nu. So that's the orbit side. On the representation side, the partition P gives us a parabolic subgroup of GONR, namely the group of blockwise upper triangular matrices with blocks given by P. And this K tuple nu gives us a unitary character of this parabolic subgroup. Actually, looks like I'm missing absolute values here. So this is a unitary character of this. And we can perform unitary induction, and the result is an irreducible unitary representation of GONR. So this is a, oops. This is an irreducible unitary representation. And very roughly speaking, this representation looks like L2 functions on O. To make this more precise, you should replace OP nu with a certain compact quotient of OP nu called a real polarization. I told you OP nu is a symplectic manifold, so locally it kind of looks like a cotangent bundle. And this polarization is maybe one way to think about this polarization is sort of picking out the X, the base of this cotangent bundle. This is kind of like X. It has half the dimension of OP nu. And instead of functions on OP nu or this quotient, we should look at the space of L2 sections of a certain Hermitian line bundle determined by this unitary character. But I don't really want to get into any of these issues. The good news about the orbit method is that thanks to the work of Kostin and Kirilov and Vogin and Zuckerman and Schmidt and many others, we know how to attach irreducible unitary representations to semi-simple orbits. So the basic techniques are real parabolic and cohomological induction. So I gave an example on the previous slide of real parabolic induction. If I had replaced nu with I nu, then we would have used this other technique, cohomological induction, to get a representation. And so, in a sense, the problem of the unitary dual reduces to the problem of attaching irreducible unitary representations to nilpotent orbits. What we want is some kind of correspondence between nilpotent orbits and irreducible unitary representations. And these representations, which we haven't yet defined, are called unipotent. representations. So of course, since the orbit method is just a conjecture, this is not a definition. Over the next few slides, I'm going to make several attempts to provide a precise definition of unipotent representations. So the first proposal comes from Arthur. Let G, without the subscript, be the complexification of GR, and let N be its nilpotent cone. Form the Langland's dual group G check. So there's this correspondence between groups and root data. Root data, recall, is this combinatorial package, consists of a root system and a weight lattice and a co-root system and a co-weight lattice. And this is a bijective correspondence. And on the set of root data, there is an involution. It's very simple. You just switch roots and co-roots and switch weights and co-weights. So this gives you a different, a dual root datum, which induces a duality on groups. Corresponding group down here is called the Langland's dual group. So let me give an example maybe. If G is GLNC, then G check is PGLNC. G is SO2N plus 1C, and G check is SP2NC. There is this beautiful correspondence between nilpotent G check orbits and nilpotent G orbits. First defined by Lustig and Spaltenstein, and then defined in a slightly different way by Barbash and Vogin. If G is GLNC, G check is PGLNC, then both domain and codomain of this map are parameterized by partitions of N. And on the level of partitions, D is just the transpose involution. So if we start with an orbit on the dual side, O check, we can define an infinitesimal character for G. So this is how it works. You take O check, you pick some E check in O check, and you form this SL2 triple, E check, F check, H check. And the element H check, and hence 1/2 H check, is well defined in its carton modulo the Weil group of G. And this carton on the dual side is identified with the dual carton on the group side. And so O check gives rise to a W conjugacy class of elements in H star, which is the same thing as an infinitesimal character using the Harish-Chandra isomorphism. So we get this, we can think of 1/2 H check as being an infinitesimal character for G. And if we have any, if you're given any infinitesimal character, you can look at all of the primitive ideals at that infinitesimal character. There's a finite number of them, and there's always a unique maximal one. And so we'll denote this maximal ideal at 1/2 H check by I O check. So here's the definition due to Arthur and as interpreted by Barbash and Vogin. A unipotent representation attached to O is an irreducible representation whose annihilator is of the form I O check for some O check mapping to O. So on the group side, we have this O. This is the group side. Here's the dual side. And we have all of these dual orbits, say O1 check through ON check, which map to O. And each of these orbits gives us a maximal ideal. And we're looking at representations of G, which are annihilated by one of these maximal ideals. And I'll use the superscript A to indicate Arthur, because we'll be talking about some other definitions as well. So unfortunately, there are only two easy examples of this definition, and I'll give them both. So if O is the 0 orbit, then there's only one choice for O check. It's got to be the principal orbit. Just to note that O prin. And hence 1/2 H check is just rho, the half sum of the positive roots. And the maximal ideal at rho is just the augmentation ideal. And therefore, a unipotent representation attached to the principal orbit is just a one-dimensional representation of GR. On the other extreme, if you start with the principal orbit on the group side, then O check has got to be the 0 orbit. And 1/2 H check is then 0. And it turns out there's only one primitive ideal at 0. I'll say more about this later, which means a unipotent representation attached to the principal orbit is just an irreducible representation of infinitesimal character 0. So this is worth remembering because I'm going to come back to this later on.
So can I ask quickly, so this, can you say again what's I of O check? So I understood there is this ideal in the center.
Yeah.
But then further, so that's the only data you're using, right?
Yeah,
so,
exactly. You would just want to require that the restriction to the center coincides with the kernel of the infinitesimal character.
I see. So it's only a condition on the central character.
No, it's also required to be maximal. That's what.
Yeah. Yeah, otherwise you get a finite collection of primitive ideals. You want to pick out the maximal one.
Right. Thank you.
Okay, so there you go. So that's Arthur's definition. The main problem with Arthur's definition is that it's too restrictive. So it excludes lots of interesting unitary representations, which I think deserve to be called unipotent. So the first issue here is that the duality map, which I mentioned earlier, is usually not surjective. So the GLN example is misleading maybe in that respect. Its image is precisely the set of special nilpotent orbits for G. And so Arthur's definition has nothing to say about non-special orbits. And yet there are all sorts of very interesting unitary representations which are attached in a certain precise sense to non-special orbits. And the best known example is the oscillator representation, or the metaplectic representation of sp2nc, which is attached to the minimal orbit, which is non-special, I guess, except if n equals 1. So maybe a smaller problem, but still a significant one, and one that I've been thinking about a lot, is that this set of representations is too small, even when O is special. So here's an example of this second problem. If GR is SLNC, then there is then Arthur, as I mentioned earlier, Arthur's set consists of irreducible representations of infinitesimal character 0. And yet there are some very interesting irreducible unitary representations at this character. This is just rho divided by n, which are in a certain sense attached to the principal orbit. Whereas this first problem has to do with non-special orbits, this second problem has to do with non-trivial covers of orbits. And this is something I'm going to come back to. So maybe partially to rectify some of these problems, Vogel introduced a much more encompassing definition of unipotent representations, which I'll quickly review. So say I is a two-sided ideal in the universal enveloping algebra. Then we can consider the quotient UG mod I. It says this is a finitely generated left UG module. UG has standard filtration, which induces a filtration on this module. And the associated graded module of UG mod I has the structure of a finitely generated SG module. So here I'm using the Poincare-Birkhoff-Witt isomorphism. An finitely generated SG module is the same thing as a coherent sheaf on G star. And we define the associated variety of I. This is called the associated variety, to be the support, the set theoretic support of this coherent sheaf. And this is going to be in general, a G invariant, also dilation invariant, Zariski closed subset of G star. And this set in its dimension provides some kind of, provides a notion of size for two-sided ideals. If I is a primitive ideal, which is to say the annihilator of an irreducible G module, then by a deep theorem of Joseph, this associated variety is irreducible, and therefore the closure of a unique G orbit O. And so here's Vogan's definition. We say that an infinitesimal character lambda is weakly unipotent, to distinguish it from Arthur's definition. For O, if number one, it's in the rational span of the weight lattice for G, and number two, it's minimal among its weight lattice coset with associated variety O. So this here, I mu, is my notation for the maximal ideal, the unique maximal ideal of infinitesimal character mu. And then we define a weakly unipotent representation just to be an irreducible one with with annihilator equal to one of these, one of the corresponding ideals, maximal ideals.
Oh, can I ask a question?
Yes.
So if you fix O, the set of unipotent representation corresponding to O, is it an infinite set or a finite set?
Yeah, I'm going to talk about that. It's typically infinite, I think, except in trivial cases. Or yeah. I mean, so here's maybe the simplest example of Vogan's definition. So say GR is SL2R. Then we can think of the weight lattice as the integers. And under this identification, the roots are identified with plus or minus 2. And let's see, of course, the Weil group is Z mod 2Z. And here, this is where this is where my infinitesimal characters live. And this is the fundamental domain of H star mod W. And if lambda is a positive integer, then there is a finite dimensional representation of SL2R at lambda. So the maximal ideal, I lambda, has finite codimension in UG, and consequently the associated variety is just 0. And conversely, if lambda is not a positive integer, then the associated variety is all of n. And so now we have what we need to calculate Vogan's infinitesimal characters. If we look at the principal orbit, then the condition is that lambda, well, it's got to be rational. That's part of the definition. And it can't be a positive integer. And it has to satisfy this minimality condition. So the absolute value of lambda should be minimal among lambda plus z, its weight lattice coset, which picks out this rational interval between 0 and 1/2. So George, this answers your question. For this, the set is infinite. For the 0 orbit, we just get the infinitesimal character 1.
But it is countable. Is it always countable, or more than countable?
Yeah, I mean, it's in the rational span of the weight lattice. Am I missing something? Yeah, I believe so. So what I want to say is that Vogan's, whereas Arthur's definition is too strict, Vogan's definition is too broad. It includes lots of representations which probably shouldn't be called unipotent. So yeah, I mean,
This was the import of George's last three questions.
Yeah. So yeah, I'm with you, George. So I think so. Oops. So as we saw in the previous example, Vogan set is often infinite, which doesn't line up with our intuition for the orbit method. We really want a finite set of representations. And another problem is that many of the representations considered are non-unitary. So here's an example. For SL2R, if you look at the infinitesimal character 1/2, which is unipotent for the principal orbit, there are two irreducible SL2R representations at that infinitesimal character, and one is unitary and the other is non-unitary. So, you know, if you believe in the orbit method, you want these representations to be unitary. So before I summarize the results of my thesis, I want to just sketch a third definition, which is ongoing joint work with Ivan Losiv and Mitya Matvievsky, which I think is a compromise between Vogan's definition and Arthur's definition, and which I think lines up really nicely with the spirit of the orbit method. So fix a G equivariant covering O tilde for O. Then we know how to class, so this ring of regular functions on O tilde is a graded Poisson algebra. And in fact, if this matters to you, it has symplectic singularities. And we know how to classify the quantizations of this ring, thanks to the work of Losiv and Namikawa and others. The quantizations are given by, are parameterized by points in some vector space modulo the action of some finite group. And it turns out there's always a distinguished quantization of this ring, which corresponds to the zero parameter in this vector space. This distinguished quantization is also characterized by the property of being the unique even quantization of this ring. Even here means admits a parity anti-involution. And like all quantizations, this quantization admits a map of filtered algebras from the universal enveloping algebra, and the kernel of this map is a maximal completely prime ideal. And so this inspires the following definition: a representation is unipotent if it's irreducible and it's annihilated by one of these ideals for some cover over O. So, well, let me also just say, if GR is a complex group, I'm fairly convinced this is close to being the right definition. And one of the reasons I'm convinced of that is that we can now show that if GR is a complex classical group, that these representations are unitary. If GR is real, then the definition almost certainly needs to be modified a little bit. Here's another reason why I like this definition. This definition is strictly weaker than Arthur's and strictly stronger than Vogan's. So under our definition includes all sorts of representations like the metaplectic representation, which are not considered by Arthur. Well, I won't write that. And it excludes all sorts of representations, including many non-unitary representations, which are considered by Vogel. So it's couched between these two definitions. So here's a picture of at least the infinitesimal characters that we get for the principal orbit of SP4R. So this picture lives inside the dual carton, which is two-dimensional for SP4R. This dotted triangle above the x-axis is the fundamental alcove. The picture on the left is Arthur's infinitesimal characters. As I said previously, Arthur attaches only one infinitesimal character to the principal orbit, and it's 0. And the picture on the right is Vogel's set of infinitesimal characters. So he attaches this full shaded in triangle. We attach just these two infinitesimal characters, 0 and 1/2, 0. So it turns out that the principal orbit has a twofold cover. The equivariant fundamental group of the principal orbit is Z mod 2Z. And so there's this twofold cover. And the infinitesimal character of the corresponding maximal ideal is 1/2, 0. Okay, so in my thesis, I study unipotent representations, mostly in Arthur's sense, but also sometimes in Vogel's sense, by restriction to a maximal compact subgroup. So I want to first describe this technique. So let KR be a maximal compact subgroup of GR. So it's unique up to conjugation by GR. Since KR is compact, its irreducibles, well, this is actually not, KR is disconnected, this is not really true, but morally, the irreducibles of KR are parameterized by integral dominant weights. And if X is a nice representation of GR, every irreducible of KR, you can prove, appears with finite multiplicity in X. And so by restriction to KR, we get this multiplicity function from irreducibles of KR to non-negative integers. And this multiplicity function captures lots of very interesting and important information about X, including the Gelfand-Kirillov dimension and the associative variety, and actually even more powerful invariance. So in my thesis, I calculate in some cases these functions for unipotent representations. So I need one more, before I actually summarize my results, I need one more notion, which is the notion of Lustig-Spaltenstein induction. Say Q is a parabolic subgroup of G with Levy decomposition L times U. So here L is a Levy factor, and U is the unipotent radical of Q. And let's say we're given a nilpotent L orbit, OL. Then we can form a nilpotent G orbit as follows. We take the G saturation of U plus OL. This is G invariant and also irreducible. And so it contains a unique dense G orbit, OG. And this function is called Lustig-Spaltenstein induction. By the way, this orbit OG is independent of U. It only depends on the Levy L. There's this moment map lurking in the background. We can form this fiber bundle over the partial flag variety G mod Q with fiber U plus OL. And the adjoint action gives us a proper surjective map to OG. Here we have, this map takes G comma X to add G X. And we say that the induction is birational if this moment map is birational. In general, it has some degree. So in my thesis, I proved basically three results about unipotent representations. First, if OG is birationally induced from OL, then I prove that the K structure of these weakly unipotent representations attached to OG is built out of the K structure of the unipotents attached to OL. And so So morally, this allows us to reduce the study of unipotent representations to birationally rigid orbits. And if OG is birationally rigid, then the codimension of the boundary tends to be large. It tends to be greater than or equal to 4. And in this case, Vogin has a powerful conjecture regarding the K structure of all of the associated unipotent representations. And I prove Vogin's conjecture in a wide range of cases. And then the third result, if OG is principal, which is a special case of 1, by rationally induced from the 0 orbit, then I give a complete classification of the Arthur unipotents attached to OG and formulas for the K-types. So in the interest of time, I'm going to focus only on the third result here, which is maybe the most concrete. Let theta be a Cartan involution of G. So this is an algebraic involution of G, and its fixed points, K, is the complexification of KR. And write G equals K plus B for the associated decomposition into plus and minus 1 eigenspaces. So I mentioned this earlier, but it bears repeating. An Arthur unipotent representation attached to the principal orbit is the same thing as an irreducible representation of G of infinitesimal character 0. And it turns out this set is non-empty if and only if GR is quasi-split. So we can make the assumption that GR is quasi-split, which means it contains a real Borel subgroup, BR. And using BR, we can cook up this distinguished Arthur unipotent representation, which is obtained by simple parabolic induction from the trivial representation of BR. And we know lots of things about this representation. This representation is irreducible by constant, I suppose, and it's unitary. And actually, we know its K-types. This is also a result of constant. We know that the K-types of this spherical principal series representation are exactly the K-types of the ring of regular functions on n intersect P. So the basic idea of my thesis is to try to build all of the other elements of this set out of SGRs for suitably chosen Levy subgroups. So to make this precise, you need, unfortunately, some more notation. I say a unipotent parameter for the principal orbit is a pair consisting of a theta stable parabolic Q with Levy decomposition L plus U, and a continuous character chi of the Levy subgroup LR, subject to 3 conditions. We require that LR, the real Levy subgroup, is split, and the differential of chi coincides with minus rho U. This is the half sum, negative half sum of roots in U. And the final condition is that U intersect P contains a principal nilpotent element. And I prove that there's a bijection between K conjugacy classes of unipotent parameters and Arthur unipotent representations. And the bijection takes a pair, Q chi, to this cohomologically induced representation. You take, I should say, S of LR. You take this spherical principal series representation for LR and you twist it by chi, this character, and then you cohomologically induce from Q up to G. And that gives you an irreducible representation of infinitesimal character 0, and every such representation is obtained in that fashion. So I want to sketch a proof of this, and the proof I'm going to sketch is a little bit different than the one appearing in my thesis. So this is a slightly more geometric argument. I mean, the first ingredient is this well-known equivalence due to Harishchandra. the category of representations of GR at infinitesimal character lambda is equivalent to the category of Harishchandra modules at infinitesimal character lambda. This already is fairly remarkable. This category on the left is defined using analysis, basically, involves topological vector spaces and continuous maps and things like that. And this category on the right is purely algebraic. We can define, using lambda, we can define a sheaf d lambda of twisted differential operators on B. This is the flag variety for G. The shifts are arranged so that if you take the global sections of d lambda, this has infinitesimal character lambda. And we can form this abelian category of k equivariant twisted d modules on the flag variety. And the global sections functor is, in fact, a quotient functor from the category of k equivariant twisted d modules to the category of Harishchandra modules at infinitesimal character lambda. And this quotient functor is an equivalence if lambda is regular. This is the better known version of the Balance and Bernstein theorem. But R lambda is 0, which is as singular as possible. And so this quotient functor is very far from being an equivalence, which is maybe why this problem is interesting. But it still has this very nice property of taking irreducibles to either irreducibles or 0. And so the set of Arthur unipotent, if we combine these two facts, the set of Arthur unipotent representations attached to the principal orbit are given by the global sections of twisted D modules with non-vanishing global sections. And so our task is to, and this is worked out in my thesis, our task is to come up with somehow necessary and sufficient conditions for non-vanishing global sections. So we know how to classify the irreducible k equivariant D modules on the flag variety. They're parameterized by pairs consisting of a k orbit Z and an irreducible twisted local system gamma on Z. So the twist here corresponds to this 0. And if we have a pair Z gamma, and we write J for the inclusion of Z in B, then the corresponding irreducible is by definition the unique irreducible subsheaf of this D module direct image, J lower shriek gamma. So this gives us all of the irreducibles. We can make this data a little more concrete and a little less geometric by picking a base point. So a base point in Z is the same thing as a Borel in G. And if we restrict gamma to this base point, we get a one-dimensional Harishchandra module, which is the same thing as a continuous character of the corresponding real Cartan subgroup. And the twist of this local system imposes this condition on the differential of the character. The d chi should be minus rho. And of course, we consider these modulo k. And my toolbar is covering this last statement, but I think what it says is that the shriek functor, if you apply the shriek functor and then take global sections, that's the same thing as performing Harishchandra module induction, at least in a derived sense. So so we want to figure out, we want to understand this non-vanishing condition. And this non-vanishing condition imposes a constraint in each simple root direction of B. And I won't spell out the details, but what these conditions amount to is that B chi comes from a unipotent parameter, as I've defined it. So this means that B is contained in some theta stable parabolic with a split Levy factor, and this chi is restricted from some character chi of the Levy. And then the argument is finished using induction by stages. it turns out this standard Harish-Chandra sheaf is irreducible, and this induction can be analyzed in stages, first from B to Q and then from Q to G. And this inner induction is real parabolic induction. And this outer induction is theta stable or cohomological induction. And so this inner induction is the same thing as chi tensor SLR, this spherical principal series representation, and this outer induction is cohomological induction from Q to G. So one really nice feature of this structure theorem is that it makes the K structure of the representations in question easy to read off. So remember the statement is that every representation is cohomologically induced from chi tensor S, some unipotent parameter. And this S, we know how to compute its K-types. I explained that earlier. This is due to constant. And cohomological induction has a very comprehensible effect on K-types. This is basically the Blattner's formula. And so we can combine these two things to get computable formulas for the K-types of all of these Arthur unipotent representations. And so that's more or less it. Instead of, I have some pictures here. I don't want to write down the formulas because they're not super enlightening, but here are some pictures for SP4R of what these K-types look like. So if you look at the principal orbit of SP4R, it turns out there are 5 Arthur unipotent representations. There's this spherical principal series S, which is always there. There are 2 limit of discrete series representations and these 2 kind of in-between representations. So the principal series corresponds to Q equals G. Here we have Q equals B, a theta stable Borel. And for these in-between representations, we have Q equals some theta stable GL2 parabolic. And K here is GL2C, which means its irreducibles are given by pairs of integers A, B, with A greater than or equal to B. And here on this graph, I indicate all of the multiplicities. So these are the multiplicities for the spherical principal series representation. Here are the multiplicities for one of the limit of discrete series representations. The other one is just the mirror image of this. And here are the K-types for the other kind of in-between representation. This one looks very different than this one. This is, if you look at the representations are related to quantizations of n intersect p, and this has 2 components. And this S representation quantizes their union, and the other 4 representations quantize one or the other component. So with that, I think I will conclude and take questions.
Can I ask a question? So
Yeah.
In your approach to defining unipotent representation, the question about your approach to defining unipotent representations that you mentioned in this work, Wasif and Matveevsky. So I heard this slogan that unipotent representations are supposed to be building blocks in classifying all unitary representations. So does that proposal fit into, this?
I don't really know yet, to be honest, Roman. I mean, yeah, I don't know if one can formulate and prove something along those lines for complex groups. Yeah, I don't have an answer to that.
Okay, I also have well, can you say a few words? What is this Vaughan conjecture that you proved? Can you say some few words?
Just proved in some cases, not in full generality, but let me write it. There's got to be a better way to scroll. So let's see. So so there is a suppose X is a GK, a finite length GK module. And I told you how to take the associative variety of its annihilator, but there's an even finer invariant, which produces a subvariety of N intersect P. So this is called the associative variety of X. This is basically the support of GER X. You choose a good filtration on X. It doesn't matter which one. You take its associated graded, gives you a K equivariant coherent sheaf on N intersect P, and you take its support. But actually, there's some finer information you can extract. You can take GER X. I mean, to formulate Vogel's conjecture, we should assume that the associative variety of X is the closure of a single K orbit. Then we can take GER X and we can, this is a K equivariant coherent sheaf, and we can restrict to O. And this gives us a K equivariant vector bundle on O. Strictly speaking, a virtual K equivariant vector bundle, because there's this ambiguity about the filtration. And more or less, Vogel's conjecture is that if X is unipotent and it satisfies, it's unipotent and the codimension of the boundary of O, closure, is at least 2, then as a representation of K, X just looks like global sections. And this K representation on the right is induced. I mean, this is the global sections of a K equivariant vector bundle, so it's just induced from some some finite dimensional representation of an isotropy group. So this is sort of easy to compute, I guess. And I prove this conjecture for complex groups under this slightly stronger codimension condition. And I also for some real groups, but nothing very general.
But in this complex case, this codimension is over complex codimension, or what?
Yeah, this is always the complex codimension.
But the orbits here are K orbits, so they're, well, it's complicated. Yeah, I mean, in the complex case, they are symplectic by accident. And so the codimension is automatically even.
Yes.
So this applies to this rigid, what you call rigid?
Yes. Yeah.
To all the rigid.
Well, did you say for all?
No, rigid. I think they probably have this big codimension.
Yeah. Yeah. I mean, there is sort of a theorem. I think Losov proves that if G is classical, maybe also exceptional. I don't remember. Maybe there's some exceptions in the exceptional. Then O birationally rigid implies this codimension is greater than or equal to 4.
Oh. So then your thing applies here. Yes?
Yeah, yeah. And this is no, yeah. That's all I want to say.
May I ask a question?
Yes.
Hi, Lucas. I really like your third definition of unipotent representation. So may I ask, like in the case when you have a birational rigid orbit, and let's say we don't take the cover, and you take this quantization by Losov, let's assume it's not special. So how would you compute the infinitesimal character?
So we do it in the classical types using McGovern's tables as input. McGovern attaches, well, he calculates all of the maximal completely prime ideals in classical types. So he attaches a finite set of maximal completely prime ideals to every nilpotent orbit, special or no, and we find a way of picking out the right one in the birationally rigid case.
Oh, I see. But what about the exceptional case? Do you have any idea?
In some cases, I mean, for example, like the minimal orbit you can use Joseph, and there are other sort of like educated guesses you can make, but no, we don't have any kind of general formula in the exceptional cases.
Okay, I see. Okay, and a second question, like you consider in the last part of the defense, you consider the principal orbit, unipotent representation supporting a principal orbit, and you show that they are all induced. So do you know general? Can you generalize it to like other induced orbit?
Yeah, I mean that's sort of the spirit of the second result that I mentioned. Scroll all the way back, but the second result is sort of exactly along those lines. So I'm trying to generalize this really nice picture for principal orbits to other not the second result, the first result. Trying to generalize this idea to other birationally induced orbits, and what I get is not really, it's not as clean. I prove more or less that every weakly unipotent representation attached to an induced orbit is some kind of, its character is some kind of linear combination of characters which are induced from unipotents attached to this orbit OL.
Okay.
But it's not induced on the nose. It's a linear combination.
Mm-hmm. Okay, thank you.
So what will you do next with your research?
Well, this definition with Losov and Matvievsky, I think, raises lots of questions. I mean, there's the question of unitarity, but I think also one thing that really interests me is trying to come up with the right definition for real groups. It's more or less clear that this definition with Losov and Matvievsky is not adequate for real groups. This is basically the problem right here. Our definition classifies as unipotent both of the irreducible representations of SL2R of infinitesimal character 1/2, and really only one of them should be called unipotent. And so there's I think this definition with Losov and Matvievsky is sort of halfway there, but there needs to be some additional constraint that's imposed to get unitarity.
So where will you do that research after you graduate?
I'm going to Oxford in the fall. Well, not going virtually. I'm not sure if I'll actually be there.
Yeah, congratulations again. You're very strong.
Thank you.
Oh, can I ask another question? So is there something special you can say about the characters of unipotent representations? Say in your definition with Losov and Matvievsky. In any one you prefer.
Characters in the sense, K characters or?
I was thinking about G characters. But that's probably...
What sort of thing do you have in mind?
No, that's fine. We can.
I don't know.
All right.
Oh, I also have a question, which I think maybe I asked before, but I don't remember if you answered it. If I have uncountable many unipotent representations.
Can you say that one more time, George?
If the number of different unipotent representations, can it be uncountable?
Just
want to understand what it looks like.
Well, under Arthur's definition and our definition, it's finite. Under Vogan's definition, we require that the infinitesimal character lives in the rational span of the weight lattice. Where did I write that? So that's a countable set. And then at each infinitesimal character, you just have a finite set of representations. Does that answer your question, George?
Yeah, but I'm thinking there's also such a notion for Peabody group of unipotent, and that case it is uncountable.
Yeah, not here, and not even under Vogan's definition.
But then I'm surprised. But this is good. Okay.
I mean, this is definitely not supposed to be the analog of your unipotent representations in the p-adic case.
No, not analog.
But you, David, once said that it's supposed to be an analog of the corresponding thing in the finite Chevalier group case. Is that? Do you still stand by that?
It's complicated. I think maybe Arthur's representations could be the best analog of unipotent in the real, the best real analogs of George's unipotent over finite fields.
In Arthur case, there are finitely many. Or
Yeah.
Arthur case, there are finitely many unipotent representations. Yes.
Yes.
Okay.
But I mean, also Lucas's new definition, that's a finite set.
But yours is different. Yours,
Yeah.
yeah, okay. But it's not unitary. No.
That's right.
Okay.
Any other questions?
Okay, I'm going to try to put the committee in a breakout room. I think that the committee members should be able to join the breakout room now. But I'm not sure.
Nice talk, Lucas.
Oh, thank you. Is that Eric?
Yeah,
Thanks.
I see you got a lot of fans here.
Most of them are non-mathematical fans.
I was guessing. I think Miggy is not a mathematical is a non-mathematical fan.
No, she's a serious mathematician.
Oh, okay.
So is Jack.
Hi, here. Say hi to Lucas. Congrats, Lou. Good job, Lucky.
Lucas, you handle yourself magnificently.
Thank you, Bert.
Congratulations.
Thank you, Bert. Glad you could join.
So am I. Really inspirational.
Great talk, Lucas.
Is that Pavel? Thank you, Pavel. Surprised you didn't have any questions. I was bracing myself.
Maybe we should ask the really hard questions now.
Yeah, with the committee gone, that's a good
Yes.
idea.
Was it a math person that was asking you about your plans for next year? Or was that a plant?
I don't know. I couldn't see the pictures, so I couldn't. I don't know.
Okay.
I have no idea.
Huh.
Congratulations, Lucas.
Who's it? Oh, who is that?
May
Long
here.
Hey, how are you?
Good. How's it going?
Good. You in Minnesota?
Yeah, still. I'm stuck here. The weather is nice now.
Good.
If you want to throw on your video, you can do that.
Yeah. Hey, hi, Lucas. It was Julia Byers who asked you about your research and where you're going to go next with that.
Okay.
Because
How are you?
Yeah, it's just amazing because I know absolutely nothing about what you're doing. I know nothing about the scribbles that you put on the screen, but the way you talked about it was so confident and knowledgeable about the subject that you really made me believe in everything that you're doing. So the committee would be insane not to pass you as
Well,
it goes.
they're here now, so maybe we should let them decide.
Oh, well, excuse me, carry on.
The committee is not insane. Yes. So we were very happy to see this. Actually, it was another thing that was a real pleasure for me, besides listening to Lucas's talk, was going through the pictures of everybody listening. There are many good friends that I don't see in the Lee Group seminar every week, and I'm grateful to Lucas for attracting them, and glad that they were able to come. Even Kiyo Nishiyama, who's, and sitting there at 3 in the morning or something, and that's commitment. So congratulations, Lucas. I will open a bottle of champagne and drink it in your honor.
Okay, thank you.
Encourage others to do the same.
Thank you all. Thank you all for coming. Appreciate it.
Thank you.
Congratulations.
Congratulations.
Congratulations, Lucas.
Bye-bye, all.
Congratulations.
Hey, Angelina.
Good night.
Angie.
Angie.
What time is it, Angie? Oh, she's gone.
What time is it, Angie?
Hey, Levitz.
Hello.
Congratulations, Luke.
You got your whole family there.
Congratulations, Lucas.
Thank you, Kiyo.
Yes, congratulations,
Bye.
Dr. Brown.
Hey, Lucas, this is your Uncle Sam. I just came back from Grandpa's. He's watched the whole thing.
Did he?
Oh.
Yeah. I don't think he understood too much of it, but he enjoyed watching you.
You can submit. You can send written questions.
Congratulations, Lucas.
Thank you,
We
Skeeter.
were all watching here.
Thank you.
Jackson was taking pictures of his screen and sending them to his friends.
Oh, really?
Yeah.
Awesome. Where's Jackson?
He's right downstairs in the living room.
Okay, gotcha. Where is that, Jack? No, who's that? Oh, that's Will. Hey, Jack.
Say hi. Say good job.